What if I told you that Earth has a second moon, which orbits Earth for the past 100 BC? You won't believe me, but this is damn true. And it is recently discovered and confirmed by NASA that Earth has a second moon named as Quasi Moon. Welcome to Luminary Cosmos. In today's episode, we will talk about recently discovered second moon of Earth, Quasi Moon. So watch this episode till the end. Also, don't forget to hit that subscribe button. So sit back, relax, and enjoy the episode. A quasi moon is not a true moon, but an asteroid that orbits the Sun in a similar time frame as Earth does. But it is only slightly influenced by our planet's gravitational pull. It is also called a quasi-satellite because it appears to circle around Earth as well. But unlike a satellite, it does not follow a simple, closed path. Instead, it moves in a complex, looping orbit that takes it around the planet, but also away from it. One such quasi-moon is 469219, Camo Oliva, an asteroid discovered on 27th April 2016 by the Pan-STARRS Observatory in Hawaii. It is named after a Hawaiian word that refers to a moving celestial object. It is not much to speak of, measuring less than 50 meters across. It circles the Earth in a rotating corkscrew like trajectory that brings it no closer than 40 to 100 times the 384,000 kilometer distance of our more familiar moon. Camo Oliva is supposed to be the most stable quasi-moon of Earth known to date. It seems to have been Earth's cosmic neighbor since at least 100 BC and will continue to follow this orbital path until around AD 37,000. According to astronomer Adrian Cofinet, who first categorized the asteroid as a quasi-moon after modeling its orbit. But how did Camo Oliva become a quasi-moon, and what makes it different from other near-Earth objects that occasionally visit our vicinity? To answer this question, we need to understand some orbital mechanics. The orbit of an object around the Sun depends on two factors: its speed and its distance from the Sun. The faster an object moves, the further away it can be from the Sun and still maintain its orbit. The slower an object moves, the closer it has to be to the Sun to avoid falling into it. This is why Mercury, the innermost planet, has an average orbital speed of 47 kilometers per hour, while Neptune, the outermost planet, has an average orbital speed of 5 kilometers per hour. Now imagine an asteroid that has an orbital speed that is very close to Earth's average orbital speed of 30 kilometers per hour. If this asteroid happens to be near Earth at some point in its orbit, it will experience a gravitational tug from our planet that will slightly alter its speed and direction, depending on how close and how fast asteroid is relative to Earth. This gravitational interaction can have different outcomes. One outcome is that the asteroid gets captured by Earth's gravity and becomes a temporary natural satellite. This is what happened to 2006 RH-120, an asteroid that was in Earth's orbit during 2006 and 2007, and 2020 CD3, an asteroid that was in Earth's orbit between 2018 and 2020. These asteroids were small enough and slow enough to be caught by Earth's gravity for a short period of time, before being ejected back into their original orbits around the Sun. Another outcome is that the asteroid gets slingshot by Earth's gravity and gains or loses speed and direction. This is what happens to most NEOs that pass by Earth at a safe distance. They use Earth's gravity as a sort of gravitational assist to change their orbits around the Sun. This can be beneficial for some space missions that want to save fuel and time by using planetary flybys to boost their speed and change their course. A third outcome is that the asteroids get locked into a resonance with Earth's orbit and becomes a quasi-moon. This is what happened to Camo Oliva, and other asteroids like it. These asteroids have orbital speeds and distances from the Sun that are very similar to Earth's, but not exactly the same. They are slightly faster or slower than Earth, which means they sometimes catch up with or fall behind our planet in their orbits around the Sun. When this happens, they experience a gravitational tug from Earth that slightly alters their speed and direction, but instead of being captured or slingshot by Earth's gravity, they enter into a delicate balance between their own orbital momentum and Earth's gravitational pull. They end up forming a looping orbit around an invisible point called the Lagrange point, which is where the gravitational forces of two bodies cancel out. There are five Lagrange points in the Earth-Sun system, labeled L1 to L5. L1, L2, and L3 are unstable, meaning that any object that orbits around them will eventually drift away due to small perturbation. L4 and L5 are stable, meaning that any object that orbits around them will tend to stay there unless disturbed by a large force. These are also called Earth Trojans because they share the same orbital path as the Earth, but lead or follow it by 60 degrees. Camo or Leva is not a true Earth Trojan because it does not orbit around L4 or L5. Instead, it orbits around a point near L3, which is on the opposite side of the Sun from Earth. This point is not stable, but it is close enough to L3 that Camo or Leva can maintain its orbit for a long time. It is also oscillates between L4 and L5 over thousands of years, making it a co-orbital companion of Earth. Gamma or Leva is not only quasi-moon of Earth. There are other asteroids that have similar orbits such as 2023 FW13, an asteroid that was discovered in March 2023 and confirmed as a quasi-moon in April 2023. It is estimated to be 50 feet in diameter and has been orbiting the Sun in tandem with Earth since at least 100 BC. Quasi-moons are rare and elusive objects because they are small, faint, and have complex orbits that makes them hard to track and detect. They are also vulnerable to perturbations from other planets, especially Venus and Jupiter, which can change their orbits over time and make them lose their resonance with Earth. They are interesting to study because they can tell us more about the formation and evolution of the solar system and the dynamics of orbital resonances. Quasi-moons are also potential targets for further exploration missions because they are relatively easy to reach and return from compared to other asteroids. They could provide valuable resources and scientific data for further space endeavors. So viewers, that's all for today. I hope you have enjoyed the content. Make sure to give thumbs up and a subscribe. So see you in another day in another episode. Till that, take care. Goodbye.